At 6 a.m. on Thanksgiving morning, nearly 300,000 people in Anchorage were jolted awake as the ground beneath them lurched without warning. Dishes crashed from shelves, walls groaned, and beds shook hard enough to erase the line between sleep and fear in a single violent second. A magnitude 6 earthquake had just struck south-central Alaska, deep enough to radiate across a vast area, strong enough to remind everyone that this city sits atop one of the most powerful tectonic systems on Earth. But this was not just another Alaska quake. What froze scientists in place was what came before it. 17 straight days of seismic silence. In a state where the ground almost never stops murmuring, the instruments had gone unnervingly quiet, as if the Earth itself had been holding its breath. Then, without escalation, without warning, the silence broke. And that is what terrified the experts. This pattern, an extended lull followed by a sharp, solitary jolt, mirrors the opening moves seen before some of history's most destructive earthquakes. Within hours, analysts were whispering a number that no one wanted to say out loud. A 5% probability that this quake could be a foreshock, not the main event. The same statistical shadow hung over Alaska in 1964, just before a magnitude 9.2 megathrust tore the region apart, killing 131 people and unleashing tsunamis across the Pacific. What deepened the unease was timing that felt almost surreal. The quake struck under the same solar and space weather conditions logged during multiple major seismic events in the past, an alignment some researchers call coincidence, and others quietly label a cosmic alarm bell. Official statements moved quickly to reassure the public. No tsunami, minimal damage, no cause for panic. But behind the scenes, the data told a more troubling story. Because when the Earth goes silent for weeks, and then speaks this loudly, it raises a question no one in Alaska wants to hear. Was this a single jolt, or the opening act of something far bigger? Under normal circumstances, Alaska's earthquakes follow rules scientists know well. The state straddles the violent boundary where the Pacific Plate dives beneath the North American Plate, a subduction engine that makes Alaska the most seismically active region in the United States. Small quakes are constant, moderate ones are expected, and even magnitude 6 events, while unsettling, usually fit cleanly into established models. Depth matters most. Quakes that rupture 7,100 kilometers below the surface, like the Thanksgiving event, are classified as deep intraplate earthquakes. Their energy spreads outward instead of upward, producing wide but typically manageable shaking. They rarely generate tsunamis, rarely cause structural collapse, and by the textbook, rarely lead to something worse. History, however, refuses to be that simple. Alaska's deadliest earthquakes did not announce themselves with chaos at first. The 1964 Great Alaska Earthquake, the most powerful ever recorded in North America at magnitude 9.2, was preceded by patterns scientists only fully understood in hindsight: stress migration, unusual quiet periods, and subtle precursors that looked harmless at the time. The rulebook also says that faults usually release energy gradually, aftershocks should decay predictably, background tremors should resume, and stress should dissipate. Yet before the Thanksgiving quake, that rhythm broke. For 17 days, the usual background hum vanished. No magnitude 2.5 or higher events, an absence so rare it immediately stood out to analysts watching the Alaska Earthquake Center's live feeds. In tectonic systems under constant strain, silence is not always calm. Sometimes it is loading. Official assessments emphasize restraint. Deep quakes, they note, often occur in isolation. Many regions experience long, quiet spells without consequence. Correlation does not equal causation. And still, the sequence refuses to sit comfortably within the rules. A long silence. Then small magnitude 3 tremors near the eventual epicenter. Then a sudden 6 rupture, strong enough to shake nearly 500,000 people. According to the models, this should be the end of the story. According to history, it is sometimes only the beginning. And when a system that usually whispers goes quiet, then suddenly shouts, it forces scientists to ask whether the rules are still holding or whether Alaska's fault lines are preparing to break them. At 8:11 a.m., On the 27th of November, 2025, seismic instruments across south-central Alaska recorded the rupture in precise detail. A magnitude 6 earthquake, centered roughly 14 kilometers west-northwest of Susitna and about 65 miles from Anchorage, tore through the crust at a depth of 80.4 kilometers. On paper, it looked straightforward, deep, distant, and unlikely to escalate. But as analysts began stitching the datasets together, the numbers refused to behave like a routine event. The first anomaly was timing. The quake arrived just 3 days after the final pair of magnitude 3 tremors that ended a 17-day seismic blackout, the longest stretch without a 2.5+ event in recent memory. That silence, followed by a sudden cluster and then a main shock, mirrored stress-loading sequences documented before several major earthquakes worldwide. Within hours, 4 aftershocks rippled through the same zone, the largest, a magnitude 3. 2. Each one a reminder that the system had not settled. Exposure models sharpened the picture. Nearly 470,000 people experienced shaking of modified Mercalli intensity 2 or higher, and 185,200 residents felt MMIV strong enough to swing lights, topple objects, and fracture nerves across Anchorage and surrounding communities. Casualty projections stayed low, a 69% chance of 0 to 1 fatality, 98% likelihood of fewer than 10 deaths. Yet hovering over those reassuring statistics was a stubborn, uncomfortable figure, a 5% probability that this earthquake was a foreshock. 5% sounds small until you remember it is the same range scientists cited, in retrospect, before 1964. More unsettling still were the gaps. Key datasets were missing in the crucial first days. No finalized moment tensor solution, incomplete high-resolution waveform records, and stress transfer models still waiting on refined inputs from GPS arrays and strain meters. Without them, scientists could not determine whether the quake relieved pressure or quietly shifted it onto neighboring faults. Some researchers layered in another line of inquiry, overlaying the quake's timing with space weather logs that showed alignment with solar and magnetospheric conditions present during other large seismic events. Official agencies urged caution, noting that no causal mechanism has been proven, and correlation alone cannot predict earthquakes. But the unease remained. Multiple independent systems, seismic networks, population shaking models, geodetic instruments, and space-based observations were now feeding into the same conclusion. Something had changed. The Earth had gone quiet, then spoken sharply, and the most important data, the kind that tells you what comes next, was still being assembled. And in seismic science, uncertainty is often the most dangerous number of all. For the people of Anchorage, the Thanksgiving quake faded quickly into routine cleanup done, shelves restocked, jokes exchanged about an early morning wake-up call. But beneath that calm, the human exposure told a far more serious story. Nearly 500,000 residents felt the shaking, and for more than 185,000, it was strong enough to rattle homes and nerves alike. In Alaska's largest city, even a deep earthquake is a reminder of proximity. The margin between a nuisance and a catastrophe can be razor thin. Inside the Alaska Earthquake Center, that margin dominated every conversation. Scientists watched the aftershocks tick in small, localized, but persistent while waiting for datasets that would take days or weeks to finalize. The absence of immediate answers created its own pressure. Emergency managers asked the same question. Residents quietly wondered, if this was not the main event, how much warning would anyone get? The memory of 1964 hangs heavy in Alaska's institutional memory, a disaster that rewrote building codes and emergency planning after a magnitude 9.2 quake and Pacific-wide tsunamis. That legacy shapes every decision now. Authorities moved quickly to reassure no tsunami, minimal damage, hospitals fully operational, but behind closed doors, they reviewed contingency plans for scenarios no one wanted to voice. Anchorage's infrastructure, built stronger than most American cities, is still vulnerable to prolonged shaking, liquefaction, and cascading failures if a larger rupture were to follow. Transportation corridors, fuel depots, and communications hubs sit on ground that has failed before. For scientists, The stress was personal as well as professional. Each missing data set felt like a blindfold, each aftershock a test of nerves. They knew the statistics favored calm, yet they also knew that rare events are, by definition, rare until they happen. For residents, the danger lay in uncertainty. Life continued, but phones buzzed with alerts, social feeds filled with speculation, and the question lingered at dinner tables. Should we prepare, or is this nothing? In that gap between reassurance and reality, millions of decisions, whether to stock supplies, review evacuation routes, or simply ignore the fear, were being made in real time. And as the Earth continued to settle, one truth became unavoidable. When the science is still catching up, people become the front line of risk. As the days after Thanksgiving ticked by, a quieter conflict took hold not in the ground beneath Alaska, but in the flow of information above it. Official statements from the Alaska Earthquake Center and USGS emphasized stability. A deep intraplate event, no tsunami risk, no signs of escalation. Those messages were accurate, cautious, and deliberately calming. But they collided with a growing undercurrent of unease inside scientific briefings and online communities, where raw data, probability models, and historical analogs were being dissected in real time. The phrase 5% foreshock probability became a fault line of its own. To emergency planners, it was a low-risk figure, not worth alarming the public. To many researchers, it was a reminder that every magnitude 9 megathrust in history began as a low-probability scenario right up until it wasn't. Internal discussions grew tense as analysts debated how much uncertainty the public could responsibly be given. Release too little, and trust erodes if something larger follows. Release too much, and panic could ripple through Anchorage faster than seismic waves ever could. Social media magnified the dilemma. Clips of the quake, maps of fault lines, and references to 1,964 spread rapidly, often stripped of context. Space weather overlays and magnetometer graphs circulated alongside speculative headlines, forcing agencies to walk a tightrope between transparency and containment. Scientists were especially careful here. No causal link between solar activity and earthquakes has been proven, and overstating correlations could undermine credibility built over decades. Yet staying silent risked letting misinformation fill the vacuum. Behind closed doors, communication teams rewrote statements line by line, weighing every word. Phrases like routine, expected, and no cause for alarm were scrutinized against evolving datasets that were still incomplete. The absence of finalized moment tensor solutions and stress transfer models meant no one could say, with confidence, whether the quake had relieved pressure or shifted it elsewhere. The result was a narrative standoff. One side urged calm and patience, the other urged vigilance and preparedness. Neither was wrong. But as the debate played out, the Earth continued on its own schedule, indifferent to press releases, algorithms, and public perception. In seismic science, the war over information is never just about facts, it is about timing. And when timing is everything, even the smallest delay can feel terrifying. Alaska's Thanksgiving earthquake leaves behind more than a shaking memory, it leaves a warning about the world we now live in. We are entering an era where earthquakes are no longer judged only by their size, but by their context. The silence that comes before them, the patterns that follow, and the layers of data that surround each event. The 6.0 Quake near Anchorage did not devastate the city, but it exposed how fragile certainty can be when critical information is still missing and history looms in the background. In a place shaped by the 1964 magnitude 9.2 disaster, even a small probability of escalation carries enormous weight. Scientists now watch Alaska through a narrowed lens, tracking aftershock decay rates, subtle ground deformation, and any deviation from expected stress release. This is the watch window, the days and weeks after a significant quake when the future path remains unresolved. Technology gives us unprecedented visibility. Dense seismic networks, GPS arrays, satellite radar, and even space-based observations feeding into models that update by the hour. Yet that visibility does not equal certainty. It only reveals how complex the system truly is. The uncomfortable truth is that modern science can detect danger far earlier than it can confidently predict outcomes. That gap between detection and prediction is where fear, speculation, and responsibility collide. For residents of Anchorage and beyond, preparedness now lives alongside normal life, not in place of it. Emergency plans remain ready, but routines continue. For scientists, every new data point is both reassurance and a reminder of what they still cannot see. And for the rest of us, Alaska's quake is a lesson in humility. The Earth does not announce its intentions. It offers clues, probabilities, and patterns, and leaves humans to decide how seriously to take them. If this was only a tremor, the system will settle. But if it was a signal, the next move may come without warning.